Am I audible, Sophie?
Yes,
Yeah. Okay, so good afternoon, everyone. Today is the 10th interaction session on structural vibration. So today we will actually go through the analysis, response analysis of MDF system under support motion, where we will see how to calculate the design lateral forces and Storey shear, and we will see different modal combination rules like absolute sum, SRSS, and CQC, and then we will move to the model reduction technique. We will see that how we can use that concept of static condensation and dynamic condensation for the model reductions. So what we will do first, we will go through how we can solve the response of a MDF system due to ground acceleration, and then we will solve one problem on pen and paper. Then we will solve similar kind of problem using MATLAB, where we will use Duhamel integral as well as Wilson theta or numeric beta, whatever that numerical technique to solve the model responses, and then we will try to calculate the design lateral forces and Storey shears, and solve some example how we can use the model combination rules, and all of this like when we will use that model combination rule, we will use that concept of response spectrum also. Already we have covered that response spectrum thing. So let's quickly start. So during last few weeks, particularly during last two interaction sessions, we are dealing with the response analysis of multi-degree of freedom systems, right? Where first we have developed the equation of motion, and then we have solved the free vibration and also force vibration case, right? So the equation of motion for the multi-degree of freedom system, so we have a mass matrix, and then the responses we can consider it either x or u, and then we have the damping matrix, and then we have the stiffness matrix is equals to some force vector. Depend on the force, where the force is acting on that particular node or the particular degree of freedom. Then we have seen that how we can decouple this equation. So but basically we have used that eigen operations, and that eigen operation leads to the omega I and the modes of information. And then once we have the model information, we use that transformation x is equals to phi into z, and finally we have this equation of motion in the model coordinates, right? Then what we have done, like we have further solved this equation, and in the model coordinates the equation of motion for each degree of freedom will leads to this equation. And where once we have the information about the modal matrix, then we can easily find out the modal responses Zn of t or Qn of t using either Duhamel integral or numeric beta or Wilson theta method. And once we have all these modal responses and modes of information, we can calculate the physical response. X is nothing but the modes of matrix multiplied by the modal response vector, right? So we have already seen and solved different kind of problems using this modal representation concept, right? So now today we will see, and particularly we use that you know forcing function or the external force at each degree of freedom. But today we will go through how we can solve a multi-degree of freedom system if a ground acceleration hit. So we have already seen what is the equation of motion for a single degree of freedom system if it is subjected to some ground acceleration minus mg xg double dot of t, right? So here the effective earthquake force, already you have developed this equation, like xg is the ground displacement, this is the total displacement of mass, and this is x is the relative displacement. So P effective ultimately comes as minus m into xg double dot. That xg double dot is nothing but the ground acceleration. So the final equation of motion comes like this for a single degree of freedom system, right? Now, if we have a multi-degree of freedom system, similarly, if we have considered that xt is the absolute displacement of each story or each degree of freedom, and ut is the relative displacement, then ultimately the equation of motion for this multi-degree of freedom system will uh, look like this: u double dot, this is the mass matrix, this is acceleration, plus c u dot, this is also matrix, and u is the vector, plus k and u is equals to minus, again the mass matrix. For a single degree of freedom system, only one mass was there, that's why we have written it like mass. Here we have the mass matrix, and then we have the influence vector and xg double dot of t. This equation of motion you can easily formulate. Now here the thing is that j is the what we call the influence vector, that actually dictates that the how the forcing function will act on each degree of freedom, right? So generally this is a vector which forms n cross 1 type of vector, where if we want to specify the forcing function will act on that particular mode or will absent on that particular mode, we can easily regulate it, right? Now, so if j, here we have used minus, then j will be plus 1 plus 1 plus 1. So for example, I want to see the influence of this force on the third degree of freedom, then I will write that 0 0 and 1 like this, or for the second node I can write the J matrix like 0 1 0 like this. So it's actually dictates how forcing function will act, or the influence of the forcing function on each degree of freedom system. Now finally, if we use this transformation u is equals to phi into z, then finally the equation of motion will look like this: I, because phi transpose m phi will be the mass or the normalized mass matrix or the modal mass matrix, and from the orthogonality property, and already we have seen that modal mass matrix is nothing but a identity matrix. So I into z double dot plus twice eta omega n z dot omega n square z is equals to minus phi transpose m j and x double dot of g, right? Now the question is, here once we have formulated the equation of motion for this MDF system, first we need to, either we can solve it using modal decomposition in the modal coordinates. So for that we need to first solve the eigen value problem, and then find out the omega and phi, and then corresponding using omega and phi, we can easily use this information and use the transformation. We can convert this equation into modal coordinates and we can solve it, right? So in the modal equation, if we use the transformation that you know x or u is phi into q, so in matrix form or the matrix and vector form it will look like that, and for nth degree of freedom u n will be nothing but your phi n and qn of t. So this is independent of time, and this actually depends on the time parameter. So finally, when we write down the equation of motion for the MDOF system under earthquake, so the equation of motion will look like Mn for the each corresponding to each mode. So Mn, it's nothing but the each component of this normalized mass matrix. That means phi n transpose m phi n, right, into qn double dot of t. So I use generally for the modal coordinates qn of t, or your course instructor has used zn of t. Both are actually the modal responses, right? So plus we have the component of the normalized damping matrix qn dot of t plus kn. That kn is nothing but omega n square omega square diagonal of your square of the natural frequencies or the frequencies corresponding to the particular mode, kn into q matrix equals to equals to minus phi n, because we have already used that phi transpose m phi, so we need to multiply it with phi transpose. So phi transpose m, we have the influence vector j and ug double dot of t. Here ug double dot of t and xg double dot of t both represents the ground acceleration, right? Now if we further simplify this equation, right, if we move the mass from that side, or we just divide it using mn both sides, so what we will left with, we will left with qn double dot t plus, so cn by mn, it will leads to twice zeta n omega n, already you have known, we know it, and km by your mn, it's nothing but omega n square. So omega n square into qn is equals to, on that side what we have minus phi n transpose m, so phi n transpose m, and we have the influence vector and ug double dot. So because this simplification will lead to a very important concept or very important parameter which we call the participation factor, and which actually tells us like influence of the mode on the final response, or the degree to which that nth or rth node participate to that total response. So we left with like j dot j matrix and a j vector, actually it's a vector containing like n cross 1, its size is n cross 1, and we have ug double dot. So ug double dot, it's a single value. Now divided by, because we have used phi transpose m phi, so we have phi n transpose m phi n, right? Phi n transpose m phi n, from here we have taken it from that side, so we now left with this equation, like this part, if we simplify it like this, minus some participation factor into ug double dot. So your participation factor leads to this equation, like participation factor, if I want to calculate the participation factor, that means that nth mode or the rth mode, we can index it like n or rth, like the contribution of the nth mode to the total response. So it will look like your phi n transpose m into the influence vector j divided by phi n transpose m phi n, and this will tells us that particularly that nth mode, how it will influence the responses. Now once we have all the modal information, we can easily calculate this quantity, what will be the participation factor for this or for due to this earthquake motion. Now once we have the knowledge of the participation factor, now we can write down the modal response qnt or znt. Either we can write it down the participation factor on that particular mode into your dn of t. The dn of t is like the response of this particular node. We can easily calculate using Duhamel integral or Wilson theta method. So the modal response ultimately comes as qn is equals to the participation factor into the dn. That means the generalized coordinates in that particular mode. Now, what will be the physical response? Physical response, we know physical response un of t is nothing but of phi n into qnt, and on also we have calculated qnt is equals to the participation factor into dnt for this particular node. So ultimately, the response, physical response, comes as your phi n, the participation factor multiplied by dn. That means the generalized coordinate uh, of this particular mode. So the u of t, or particularly if I want to calculate for a particular node, then the equation will be phi n, the participation factor corresponding to that particular mode, and dn of t. That is the response or the generalized coordinate response in the generalized coordinates. So total response, if I want to calculate the total response u of t, so it will comes as a vector. So it will be nothing but summation of I is equals to 1 to n your this quantity. So the participation factor, mode shape information, and the response of this particular corresponding to the particular degree of freedom. So by this way, we can calculate the responses corresponding to different modes when a earthquake is, or a MDF system is subjected to an earthquake. So by this way, using the modal representation, we can solve it. So now that was the responses, right? We have found out the U of t, physical responses. U of t, that means the displacement corresponding to that degree of freedom, different degree of freedom of the generalized coordinates. So now how we can calculate the equivalent static force? So for a single degree of freedom system, we have seen that equivalent static force Fs of t is nothing but k into u of t. Once we have the information of u of t, that means the responses, we can calculate the equivalent static force. So for a single degree of freedom system, we have seen that okay, the equivalent static force is nothing but k into u of t, and further we have simplified k is nothing but m into omega n square into u of t, and finally leads to m into a of t, and a of t is nothing but the pseudo acceleration, because we have used the information of the that response breakdown, right? So now for the multi degree of freedom system, similarly the Equivalent static force associated with the nth mode is represented by this, like Fsn of t, particularly corresponding to that particular node k into un of t, right? Now further we can simplify this equation like if Sn of t is equals to k, we know k is equals to omega n square into m multiplied by u of t. Already we have calculated, like u of t is nothing but phi n into the participation factor into dn. So you can use this information here, participation factor phi n into dn. So what is the physical meaning of this participation factor? It will tell that particularly nth mode, how that nth mode will contribute to the final response quantity. Now if we simplify it further, we will have that equation f Sn of t. That means particularly for that node, the equivalent static force will be the participation factor multiplied by omega n squared dn m into phi. Now further we know that omega n square into dn is nothing but omega n square into dn is nothing but the pseudo acceleration an, right? So because we are using that pseudo acceleration, because we will use the information from the response spectrum analysis. So finally, like our uh, that equivalent static force corresponding to each story, if Sn of t we can calculate once we have the participation factor. We need to calculate the pseudo acceleration. Either we can calculate using like omega n square into dn square, or we can easily calculate it from the response spectrum curve. We will see how. M phi n. So finally, that equation, if we solve this equation, we can easily calculate the value of fsn corresponding to each node. Like when we will solve one example, then we will see step by step how we can use this equation and solve this. Pen and paper we will solve just a few minutes back, a few minutes later. Okay, so once we have the information of the equivalent static force fs, we can easily calculate the base shear. Like for the single degree of freedom system, the base shear we have calculated like this. Base shear is nothing but k into u max, and we have further simplified that equation, like k into u max is nothing but your spectral displacement, and k multiplied by spectral displacement. So k further we can simplify it like m into omega square into sd. Now what will be the base shear? So base shear will be like this for the single degree of freedom system. And base moment of base is nothing but that your f, whatever we have calculated, that means the for the linear system the base shear multiplied by the Storey height h. So already we have seen how we can calculate and use this information for a single degree of freedom system. Now for a multi degree of freedom system, similarly we can use the information. So for a multi degree of freedom system, like here we have the Storey shear fs1, fs2, fs3. Like how we can calculate the Storey shears, already you have seen here, like using this information, the participation factor, the pseudo acceleration, mass, and the mode shape information for this particular node. We can use this equation also, same equation, to find out the equivalent static force at each story. Now once we have this equivalent static force, we can use this information to calculate the base shear. So vb of t, the total base shear will be nothing but summation of, say, I is equals to 1 to n your r of t, the influence vector r or j, whatever you can write, and then f I of t or f si of t, that will be the total base shear for this structure, right? Now this influence vector, for here we can use generally a identity vector, so that we can count the effect of Storey shear on each mode to calculate the base shear, right? Now base moment, similarly, once we have the information of the if SI, we can easily calculate the base moment also. MB of T is nothing but total MB is nothing but summation N is equals to 1 to, say, I is equals to 1 to N, your XI, FI of T or FSI of T. So using these two informations, we can easily calculate the base shear and base moment corresponding to each mode. So now let's quickly solve one example. Then we will come back here and see like how we can use this information for the modal combination rules. So here, let's quickly solve this example. Pay attention so we can easily correlate how we can calculate this thing. So calculate the response of 2D building using the modal superposition. So here the building is shown. The shear building model is given here, where masses are given mm, and the m value is given as 20,000 kg and k is given as 18 into 10 to the power 6 Newton meter. So first what we need to do, we need to formulate the mass matrix and the stiffness matrix for this shear building model, right? So the mass matrix will be, we know it's a diagonal matrix m1 m2. For the k matrix, we need to formulate it like k1 plus k2 minus k2 minus k2 k2. So k1 plus k2, and already we have formulated this thing here. So m matrix looks like this, and the k matrix looks like this. Now once we have the mass matrix and the stiffness matrix, now what is the next step? We need to do the eigen analysis. Why? To calculate the omega I and phi, right? So how we can use that eigenanalysis? So we need to first formulate the characteristic equation k minus omega square m is equals to 0. We need to just solve this determinant of this equation. So here, look, you just need to do the calculation, or you can use the MATLAB to find out this omega 1, omega 2 and corresponding mode shapes. But still you want to, you need to solve it by pen and paper, and you need to get habituated with this, because during the exam, you will not get the liberty to use your MATLAB, right? So now determinant is simple. You need to multiply this into this and minus this into this. So finally we have this equation, and I have calculated omega 1 is equals to 19.02, omega 2 is equals to 47.77 rad per second, rad per second, right? Now once we have this omega information, that means the, you know, after doing that eigen analysis, we have the eigenvalues. Eigenvalues are nothing but lambda 1 and lambda 2, omega 1 square and omega 2 square. Now what we need to do, we need to find out the corresponding eigenvectors for corresponding to these two eigenvalues. So that will lead to the mode shape information. So first, for the omega 1 is equals to, if I use omega 1 is equals to 19.02. So if I use that omega 1 square, or directly we can use the omega 1 square value. So first modal information, first mode shape comes as like here the, if you use omega here in this equation instead of omega square, first you need to use omega 1 square, and then in the second equation you need to use omega 2 square. So first we have used the omega n square, and the matrix look like this, multiplied by phi 1. That means phi 1 content your modal information regarding phi 1 1 and phi 2 1, right? Or we can write it down like this: phi 1 is equals to phi 2 1 for the top story, and phi 1 1 for the second story. So you can use this. This will, make that or may manage that consistency, right? So finally we have two equations. Now we need to normalize it to 1. So for phi 2 1, I have considered it 1, and you also need to consider for the last mode, you need to consider it 1. So once we have this, we have the phi 1. That means the first mode shape information. It's like In phi 21 it's 1, and phi 11 is 0.61. So the first mode shape we have obtained. Now similarly, for the second mode shape we need to perform the calculations, similar calculations, like for omega 2 is equals to this. That means you need to use omega 2 square in this characteristic equation, and you will find out these equations, right? For the second mode phi 2, that means phi your 21 1 2 and phi 2 2. So phi 2 2, consider that phi 2 2 as 1. You have I need to calculate phi 1 2. So phi 1 2 comes as minus 1.61. So here is the second modal information. So phi 2 2 is equals to 1, and here phi 1 2 is equals to minus 1.61. So till now what we have done, we have the information about the natural frequency. We have omega 1, omega 2. We have phi 1 and phi 2. We have the two frequencies, and corresponding to that frequencies we have to mode shape. Now what we need to do, we need to use that modal representation to solve this equation. So before that, what we need to do already, we have discussed, like first we need to normalize the mode shape with respect to mass normalization, because uh, if we use that normalization thing, that will, like when we will solve using MATLAB or any computational facility, it will less heavy and lead to better convergence. So normalized mode shape, we know how to do the mass normalization. Say phi I want to normalize that ith mode. Say it will be nothing but phi I divided by under root of phi I transpose m phi I. That means, what is that? That is mn. That means, or I, because we are indexing at I, so it is nothing but ith component of your modal mass matrix M. And it is ith component, we can easily calculate once we have the phi information. So normalized first mode is phi 1 divided by under root of phi 1 transpose m phi 1. So phi 1 we have 0.61 and 1, and phi transpose m phi, if you perform this operation, it will come as this. So phi 1, that means normalize first, mass normalize first mode shape come as this, mass normalize second mode shape comes that. Once we have that two mass normalized mode shape, we can easily calculate the modal matrix. So modal matrix content your information about phi 1. This is nothing but your phi 1 and phi 2. So this is your phi 1 and this is your phi 2, phi 2, right? Now once we have this mass normalized mode shapes, we can easily calculate the participation factor. Participation factor for each node, participation factor qi, or not qi, we have denoted it using this, is nothing but phi I transpose m r or mj, the influence vector, divided by phi I transpose m phi I, right? And that actually, if we simplify this equation, that actually we can write it down like this. The participation factor is nothing but Li by Mi. Now what is that Li quantity? That is actually the modal mass. Li is nothing but the modal mass, phi I transpose m into r. Okay. Now once we have all the information, we can easily calculate phi 1 and phi 2. That means the modal participation corresponding to two modes. So in vector form, how it will look? It would look like phi transpose, that big phi, that modal matrix, phi transpose m r divided by phi transpose m phi. So ultimately phi transpose m phi will be a diagonal identity matrix. It will be 1, and the calculation will be easy. So phi 1 and phi 2, either you can calculate it separately using this equation, or you can use the whole information of the mode shape to calculate the participation factor. So first, the participation factor corresponding to first mode comes as this 194.2, and the participation factor corresponding to second mode come as 45.6. Now once we have the participation, now we can calculate the modal response. Now the modal response, what is the how we can calculate the modal response? The modal response already you have seen, like for the earthquake here, u of t is nothing but phi n corresponding to that mode shape. The information about the your modal participation factor and information about the responses or modal coordinates in generalized coordinates, what we can easily solve it using dual integral or other numerical integration technique. So here if we use this information, so u1 of t will be, that means u1 of t, that means what is that u1 of t, that means the displacement corresponding to first degree of freedom, right? So what will be the equation? So u1t will contain two information. One will be u11 of t, that means corresponding to first degree of freedom. This is u1 of t, this means displacement corresponding to first mode, right? So that was the first mode. So u22 of u12 of t, sorry, u21 of t. So we need to calculate it for two values. So what will be that? The participation factor multiplied by phi 1 into d1 of t. Because already we know that u1 of t is nothing but participation factor for this particular mode into the mode shape into d1 of t, the response. Now here phi 1, we have the participation factor for first node. It comes as 194.2. We have the mass normalized mode shape and we have the value of d1t. So now the thing is how we can calculate this d1t. This d1t either we can calculate using numerical integration method, like dual integral and all other technique, or we can use the response spectrum to calculate this g1 corresponding to that omega 1 and zeta 1, right? It's a function of omega 1 and zeta. So for now we are considering, okay, d1 we need to calculate. Okay, now for second node, so here u1t will give us two responses. Here you can see u11t this and u21 of t this. So for example, for the first mode, the maximum displacement is occurring here. Say we have numerically solve it, and u11 of max coming as here and u22 max is coming here. So for the first, just try to understand, for the first mode we have calculated the responses. Similarly, for the second mode we can also calculate the modal responses. U of t is nothing but the participation factor mode shape into the responses, or the modal responses or the generalized coordinates, whatever we want to say. So that comes as like this. So that u2, that means the response due to, or the displacement response due to the second mode. So that content u12 and u22, right? U12 and u22. So here this response and this response, let's consider the maximum response is occurring here, and for this maximum response is occurring here. The fact is, like, for each degree of freedom, the maximum peak responses will not occur at the same time point. It may occur in different time points. Say for example, for this condition, here the maximum response occur and here the maximum response occur. It maybe the maximum response here occur will here, and for this maximum response will occur here. So it might be in different time step, might be in different algebraic sign. So that how will be the total response, what will be the total response? So we have already calculated u1 of t, that means the response due to first mode, and here we have calculated u2 of t, the response due to second mode. Now tell me what will be the total u of t. you need to sum them up, right? Sum this response, your u21 plus u22 and your u11 plus u12. Then only you will get the total response due to that two mode shapes, right? So the total response here, now we will face the next problem. Like total response, first solve the total response u of t, obviously. So that was the 2 degree of freedom system. The total response will contain here one response total, here one response total. That means u1 of t and u2 of t due to first mode plus second mode. So here first mode, for the first mode u11t plus u12t, for the second mode u21t. That means this is the first modal information, this is the second modal information. What we need to do, we need to sum them up to get the total responses. That means what we are doing here, we have found out that u21, here we have found out u11. So for this first story or first degree of freedom system, what will be the total displacement, we need to sum them up. So this plus this, precisely we have done here this. So finally, the equation will look like u1t and u2t is nothing but u11 plus u12 and u21 plus u22. Just you are adding the displacement, modal displacement of that particular mode. So that comes as like this. So this will be the total response. Now we have solved it. Now the total response will look like this, like say u1 of t, the displacement corresponding to the first degree of freedom. This is the t ordinate, this is u of t, and say u2t will also look like this. The final response t versus u2t. This is the displacement due to first story. This is the displacement due to in second story due to the two modes, considering two modes. Now here the problem is d1, d2, the peak values. We can easily calculate it using either we need to solve it numerically and then we need to look for the maximum response, or we can use the response spectrum method to find out the peak responses. We can easily find out the SD value corresponding to omega and zeta, right? And precisely if we do it or substitute the value here, we can easily calculate the responses easily, right? So we will see. Now the thing is, one more major problem we have seen here, like we have calculated the modal responses for the first mode, for the second mode corresponding to the degree of freedom. Now how we can add them, how we can um, do the modal combination to get the responses, because we have seen that the peak responses for the different story and for different modes will occur or the can occur at different time points. So what sort of rules we should follow so that the final estimation will give us the better result, or the accurate result more precisely. So what we need to do, how to add them here? We have added linearly, right? We have added directly linear combination we have used. Like we have just added these two, like u of t is nothing but just add them to u1t and u2 of t, and we get this. But this is not like correct at each time point, because we have seen that different peak responses will occur or can occur at different time points. So we have some sort of rules, like we have the SRSS, absolute sum, and CQC. We will see what actually they means. So before that, we have already seen the concept of the modal mass. So in that example, if calculate, if someone want to or someone asks you to calculate what will be the modal mass corresponding to that two modes, because we have two natural frequencies omega 1 and omega 2, we have two modes. So what will be the effective modal mass? So effective modal mass, already we have seen effective modal mass for nth node will be nothing but your phi n transpose m into your influence vector divided by phi n transpose m phi n. That, so that is the effective effective modal mass corresponding to each mode. So if I want to calculate the effective modal mass corresponding to first mode, what I need to do? M effective corresponding to first node will be phi 1 transpose M into R or J divided by phi 1 transpose M phi n. So we have all the information about this and this. So finally, the modal mass corresponding to two modes comes as these two. The total effective mass will be, you just need to add them, or you can use this equation. So that's why that Ln we have abbreviated earlier, that actually gives us information about the modal mass, because when we will consider the responses, first what we need to do, we need to consider that modal mass, or the 90% of the modal mass. We need to consider the modes up to that 90% of the modal mass should be considered. So now if we come back to this equation again, and try to correlate that with that modal mass thing, so finally u of t we have is nothing but summation n equals to 1 to, or better indexing I equals to 1 to n phi I and di of t, right? So the thing is, for this example we have seen we have only two modes. In MDF system we can have n number of modes. Now the thing is, how many mode we should consider for our calculation, so that the calculation will be accurate. So for this we need to use the concept of the modal mass, and the modes which actually contribute more than your 90% of the modal mass. So number of modes which actually contribute to the 90% of the modal mass, we need to consider up to that mode. So for example, generally for the fifth, if we consider up to fifth mode, it actually actually combine the 90% of the modal mass. If we consider up to eighth node, it will actually give us that okay, that the modal mass will be more than 95% or 95%. That's why we need to have the information about the modal mass. So modal mass is nothing but what we have seen, Mi is nothing but phi transpose Mr. We can easily calculate the modal mass like this. So here already we have calculated the modal mass, and now let's like find out how we can add the responses to get the total response. So what I have said here, like how we can use this information to add this to, like this is the response due to first mode, displacement due to first mode, and this is displacement due to second mode. But what we need to do, we need to find out the total displacement. That means this is u1 of t, this is u2 of t. Now I need to calculate u2 of t total. So here what we have done, we have directly add them. That means we have used that linear superposition concept. But every time it is not accurate, because different peak responses will occur at different time instance. So there are some rules, like the absolute sum rule. In absolute sum rule, what we assume that all modal peaks occurs at the same time and the algebraic sign is ignored. We have considered that okay, all the peak values will be response, or the peak response will occur at the same time. So we can easily calculate the maximum of r of t is nothing but just add them, that n equals to 1 to n maximum of mod of r of t, or this is x of t, right? That means we are Neglecting the algebraic sign, we are using the mod. Say for example, the peak response minus 10 and 10, we will consider that and we will add them up. This is called the absolute sum method. That means we are adding them, but we are ignoring the algebraic sign, because the response, in response, this is the response. Okay, so here maybe you say 1 1, the maximum response occur at say 10 centimeter positive. Now maybe you 2 2, the peak response can occur here on that direction, say minus 8 centimeter. Now in absolute sum method, what we are doing, we are just adding them, absolute values, adding the absolute values. So here we are considering that okay, the peak responses are occur at the same time point. Say if it is occurring at 10 second, it will occur at 10 second, and we add them and we neglect the effect of the algebraic sign. Now we have second method, square root of sum of square, SRSS. Here what do we do? We just square root of sum of squares, right? So we use the square of the peak values, then sum them up, and then we will if we perform the under root, we will get the maximum response at each time. So we will see how we can use this information to get the story share, the base share, the base moment, and the responses at different nodes. So before that, what I have already told, that this maximum responses, either we can calculate it numerically or we can use the information regarding the response spectrum. Recall what was the response spectrum? It was the uh, plot of the maximum responses of a single degree of freedom system as a function of time period and for a particular earthquake and for a particular value of damping. And already we have seen that what are the relation between spectral displacement, spectral velocity, and spectral acceleration. So here we have all the information. And for a corresponding earthquake, so the input will be given, earthquake will be given, the damping ratio of the structure should be there, and omega I we have. So we can easily calculate the maximum values and we can use them to calculate the responses of different stories. Like here, the peak value of the nth mode we can easily obtain from the response spectrum. So un of t, what we have already calculated, it's nothing but the participation factor phi n into dn of t, right? Now this dn of t we can calculate it from the response spectrum analysis. How we can simplify this equation? Like un of t, we know that participation factor phi n, and dn is nothing but your an, spectral acceleration, divided by omega n square. Now what will be the maximum of this? Maximum of un of t, the maximum of un of t will be nothing but your participation factor divided by corresponding your modal information, then your uh, now that n by omega n square, either you can use like this sd corresponding your omega n zeta n, or 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 you can use like this, because we have the equation of spectral acceleration and displacement both, so we can easily use this equation in two ways. Like maximum of u of t will be the participation factor, the modal information, and your spectral displacement corresponding to that particular omega n and zeta n, right? We can easily do it. And instead of displacement, if we want to use the acceleration curve, we also can do it. Like maximum of un of t will be nothing but the participation factor divided by omega n square, because an or your structural spectral acceleration is equals to omega n square into d sd. So sa omega n and zeta n. So if your value sa value is provided for this particular uh, frequency and the damping ratio, we can easily calculate it. Similarly, the maximum u dot t is nothing but sv and maximum u double dot t sa, right? Similarly, instead of a displacement, you need to use the spectral velocity. Instead of acceleration, you need to use the spectral acceleration. So if we have the information about omega I, zeta, we can easily calculate the SD value for corresponding that. Now, once we have this SD value, that means spectral displacement value, we can easily solve it. Like here, precisely, in this calculation or in this problem, we will solve it step by step, each and every step, from the beginning to end, base shear, Storey shear, all the calculation, including your or including your response spectrum analysis concept, like how we can use this concept and use it, right? So just pay attention to this problem. If you just just pay attention for 10 minutes, you will understand the whole concept of this interaction session. Okay, so here, calculate the maximum response for displacement. What we need to found? Displacement. We need to find out the lateral force, overturning moment. Three things. We need to find out the response u of t. We need to find fs. We need to find out the m. We need to find out b. All those things. Okay. Lateral force, also base shear. At base shear also. Okay. So we have 3 degree of freedom system. Just now pay attention. We have 3 degree of freedom system. We need to solve for these quantities, right? How we can do it? So first we need to form the mass matrix. So here 3 degree of freedom system. The mass matrix, we know mass, it's a diagonal matrix. So M1, M2, M3. So here M1 is given as 2 kg, M2 1.5 kg, and M3 is 1 kg, right? So okay, it's like not kg, it's giga, in giga. That means in kg it will be, you need to multiply 10 to the power 6 to convert in kg. So gigagram, it's like, so okay, no issue. You just need to multiply 10 to the power 6. Now you need to form the K matrix. So for the 3 degree of freedom system, the K matrix will be K1 plus K2 minus K2 0 minus K2, K1 plus K2 plus K3 minus K3, and minus K3 K3. So we have all the value K1, K2 and K3. It is given as mega Newton per meter. Okay, so we need to convert it into from mega Newton to Newton meter. So 10 to the power 6, you just need to multiply it. So mass and stiffness matrix is ready now, right? Now what we need to do? Step 2. So step 1, you need to uh, get the system matrices. So mass and stiffness. We have all the mass and stiffness information. Now the Storey height is also given 3 meter, 3 meter and 3 meter. So step 2, what we need to do? We need to calculate the omega and the mode shape information. So for that, what we need to do? We need to go for the eigenanalysis. That means we need to formulate the uh, characteristic equation k minus omega square m, and we need to solve the determinant equal to 0. So after solving it, it's a little lengthy calculation, but it's very simple. So that was the final equation, and the lambda 1 comes as 21.08, lambda 2, that means these are lambda, that means these are nothing but omega 1 square, this is your omega 2 square, and this is your omega 3 square. I will suggest you should also do the same exercise on pen and paper step by step, so that you understand the process and step how we can solve it easily, effortlessly. So once we have this information, we can easily calculate omega 1, omega 2 and omega 3. So first frequency comes as 4.59, second is comes as 9.81, and third frequency comes as 14.57. Now what we need to do? We need to find out the mode shape. Phi 1, phi 2, phi 3. Phi 1 corresponding to your omega 1, phi 2 corresponding to omega 2, phi 3 corresponding to your omega 3. That means again we need to formulate the characteristic equation. That means a minus lambda v or I lambda, V is equals to 0. That means your K minus omega 1 square M is equals to, or multiplied by phi 1 is equals to 0. And phi 1, we know it's for the three modes we have. So phi 1 1, phi. Oh, okay. So for first I have calculated for third mode. So it's okay, no issue. You can do it for here also for the first mode, phi 1 1, phi 2 1, phi 3 1. So you can do it for the that mode also. So here I have started with the third mode, right? Corresponding to third natural frequency, omega 3 is equals to 14.57. You can start with the first mode also, no issue. So third mode, I have started with that third mode. So here 513, 523 and 533. So we have three equations. Now what we need to do, we need to consider that, okay, 513 is equals to 1, and we need to solve for the two rest of the two equations. And the third mode, the mode shape is comes as 1 minus 1.042 and minus 0.40. Similarly, you need to calculate for lambda 2. That means you will get the phi 2, and for phi 1. So now we have phi 1, that means first mode shape matrix, phi 1 1, phi 2 1, phi 3 1. We have phi 2, that means second mode shape. So phi 1 2, phi 2 2, phi 3 2. And the third mode shape, phi 3 3, sorry, phi 1 3, phi 2 3, phi 3 3. Right? Now what do we need to do? We have now we have omega information, we have phi information. Now we can easily calculate the uh, mm, modal participation factor. So before going to the modal participation factor, here in this problem uh, says we need to consider 2% damping for each for the first two modes, and we need to use the classical damping or the Rayleigh damping model to calculate the damping matrix. So let's first formulate the damping matrix. So recall the Rayleigh damping model. Zeta n was half a0 by omega n plus a1 plus by 2 into omega n. Like we have a0, that mass dependent coefficient is nothing but zeta 1, that means proportional to your omega 1, and a1 is inversely proportional to your omega 1, zeta 1 divided by omega 1. So if we use the model, we can easily calculate zeta 1 is equals to 1%. So what will be the value of zeta 2 and zeta 3? Use the model, you need to calculate a0 and a1, and once you have the a0 and a1, you can calculate the value of zeta 1, zeta 2 and zeta 3. Just go through the previous lecture videos, you will find out that we have elaborately explained these models. Along with Rayleigh damping, I also have explained the Koff damping model. So you just go there and see, there we have solved so many problems. So first 2%, 2.6% and 3.5%. So they have said that for the first mode, use that 2% and calculate it using your Rayleigh damping model. So we have the zeta 1, zeta 2 and zeta 3 value. That means we can easily calculate the or form the C matrix, right? So now what do we need to do? C matrix, after having this C matrix, we need to calculate the participation factors. So participation factor, here we have three modes, so we will have three participation factor. So phi n participation factor, that we know it's nothing but phi n transpose m r. R is the influence vector divided by phi n transpose m phi n. So here we will use the influence vector 1 1 1. That means we will consider that influence at each mode. So simultaneously, you can easily calculate what will be the modal participation factor for first mode, because we have the phi informations. Similarly, so that comes as 0.43 phi 2 that comes as 0.36, and similarly phi 3 that comes as uh, 0.21. So we have now the participation factor ready. Now we can easily calculate the value of the responses. Now for this question we have like natural frequency, go there. We have three natural frequencies, we have three damping values here, three damping values. So corresponding to three natural frequency and three damping values, we need to find out the spectral acceleration or displacement to calculate the displacement response, because the displacement response here we have seen that either we can calculate it using SD or SA. So generally we use the spectral acceleration values, or the spectral acceleration values are generally given. So we will stick to that spectral acceleration. So corresponding to omega 1 and zeta 1, it gives us this. Corresponding to omega 2 and zeta 2, we can have this. Corresponding to omega 3 and zeta 3, we have this. Now once we have the information of the participation factor phi 1, 2 and 3, and we have SA1, SA2 and SA3 value, we can easily calculate the maximum modal responses. So what will be the maximum modal responses? The maximum modal responses for first mode U1 is nothing but the participation factor divided by omega 1 square phi 1 into SA. Like we have already seen how from where we are getting these equations. So from here we are getting the equations, right? Now we can easily solve it. So what will be the maximum U? This. Now U1 maximum of U2, similarly this maximum of U3 comes as this. So we have U1 maximum, U2 and U3. Now we need to add them. So we use SRSS to calculate the maximum displacement. SRSS, already you have seen that we need to sum the square of the maximum displacement. So here maximum of U as per SRSS will be for this first, that means you have this one, that means U11 square plus for 2 this one U12 square plus U13 square. For the second component again, for the third again. So we have all the information, U11, U12, U13, again U21, U31 plus U22 plus U23 plus U32 plus U33 square. So look, we have all the information. Maximum of U. So this is your U11, this is your U21, this is your U31. Again, so if we solve this, we will have the maximum responses. This. So clear, Sovik? Do you have any kind of questions?
No.
Yes. So we just, how we add uh, the responses obtained from each mode using the SRSS. Now we can use like absolute sum method. For the absolute sum method, we just need to add the absolute values like 48 plus 27 plus 9, like this. We have CQC rule also. So we will see that later. So first, till now we have solved for U. That means what will be the displacement. Now we can solve the lateral forces too. So let's quickly solve the lateral forces for these three modes. So the lateral forces, we know already, you have seen the equation, like maximum of F of t lateral force due to first mode is nothing but K multiplied by your response in first mode. So we have all the information, we have the K matrix ready, 300, minus 200, 0, minus 120, 180, minus 60, 0, minus 60, 60. And we have also U1T information. U1T, that is the modal response due to the first mode. That means here U1T, maximum of U1T, these informations, right? So we can easily use them. This is, so you can easily calculate what will be the maximum of F1T, just do the matrix operation. Likewise, you can calculate the F2T and F3T. So what will be that? K for the F2T, what do you need to do? K matrix multiplied by that maximum displacement for the second mode, whatever we have calculated, and for it, what we need to calculate? K multiplied by UT3. Now, once we have for this three, that the lateral forces for the three modes, for the three stories, like here, this, and this. Say for this is first mode, we have again lateral forces values like this, and say this for the second mode, and again we have the lateral forces values like this, or this in third mode. So we just need to sum them up to get the total or the final lateral forces. So here we will use again SRSS. So SRSS, that means you need to sum the square of the maximum values. So this is the F11, this is F21, this is F12, this is F13. Likewise, for the three modes, we can easily calculate. So this is nothing but your F1 of T. This is your comes as F2 of T. This is comes as F3 of T. Right? So by this way, we can easily calculate the lateral forces acting on each story due to different modes. Clear? So Storey shear, here you can see the values whatever we are getting here. So the values I have plotted here. So now we can easily calculate the base shear. So we have calculated the lateral forces. Now we need to calculate the Storey shear or base shear for the single degree of freedom system. Here we have different stories, so obviously that will be Storey shear. So what will be the Storey shear information? The Storey shear information we can easily calculate like same thing. V1 is V11, V21, V31, V2, V12, V22, V33, and V3. So here already we have calculated the forces acting on each level. So from this here we just need to add them up. Like here 2.44 plus 3.33 plus 3.3 for the first V1. So comes as like 9, 6.6 and 3.3. Likewise, we can calculate the Storey shear for the rest of the two modes. And once we have the Storey shear information, we can use again the SRSS rule to find out uh, the final Storey shear at each level. And once we have the Storey shear, what do we need to do? We need to multiply with the height. That Storey shear Vt into height will give us the moment. So moment will be nothing but your Storey shear at each level into the height of the stories. So here you can see for the first, for the second, for the third, and similarly, if you complete the rest of the two exercise, you will get the moment or the Storey moment with respect to different degrees of freedom. So by this way, we can solve the complete problem. Now it's time consuming and lengthy. We generally do it using MATLAB. I will show you how we can easily calculate it using MATLAB. So till now, what we have calculated, we have seen the, what will be the response of a multi-degree of freedom system due to some ground motion, how to use the concept of the participation factor, And the participation factor, the significance of the particles participation factor, we have seen that particularly that which mode will consider how many, the consideration will come from that particular mode. We will see all these things. Now we will solve few more examples, and then we will move to the MATLAB to solve the similar kind of problems using MATLAB or using Duhem electrical and Wilson theta method. So first let's quickly solve few example, and then we will go and solve this. So the mass and the modal matrix for the MDF system. So here two DOF system is given. Mass is given as 200 and 100. Mode shape informations are also given. The influence matrix is also given, right? Influence matrix J also influence vector. Sorry, vector is also given. Now calculate the modal participation factor 1 and phi 2. What do you know? Modal participation factor for first node will be phi 1 transpose M into R or J, your influence vector, divided by phi 1 transpose M phi 1, right? Similarly, the second participation factor will be phi 2 transpose M influence vector divided by phi 2 transpose M phi 2. So first you need to find out what is the value of phi 1. So here the total mode shape matrix is given. This is your phi 1. So phi 1 is 0.5 and 1. What is the value of phi 2? Minus 1 and 1. Now what is the value of J? Is given 1 and 0. That means only the first mode, the contribution uh, uh, given to that, to the first mode. Now do the operations. So phi transpose will look like this: 0.51, and this is the mass matrix. This is your influence vector R or J, and if you calculate phi 1 transpose M phi, that comes as 150, and that leads to first participation factor 0.67, second participation factor minus 0.67. So we have calculated two participation factor like this. So if n number of modes are given, we can easily calculate the participation factor corresponding to that n number of degrees of freedom, right? Now here another question, like for a two-story building, again the mass and the modal matrix is given. The natural frequencies are also given. For the first mode it's 5.12 rad per second, corresponding to second mode it's given as 14.44 rad per second. The corresponding acceleration response are also given. That means your SA values are also given, right? Now consider the influence matrix J minus 1 1, given G is equals to 9.81. Calculate the modal participation factor for first two modes. Again, participation factor for first mode phi 1 will be phi 1 transpose M J divided by phi 1 transpose M phi 1. So what is the value of phi 1? This is your phi 1. Phi 1 is minus, that means first mode shape minus 0.024 minus 0.045, and phi 2 is minus 0.037 and 0.029. Mass matrix is given. You can easily calculate it. You can easily perform these calculations. Use MATLAB or use calculator to do this vector and matrix calculation. First do this operation and then second operation. So the first participation factor comes as 27.86 and the second participation factor comes as 8.60, right? Now all the things are given, like natural frequencies are given, what will be the corresponding spectral acceleration values are given. So now we can also find out the other quantities, like calculate the design lateral force at the second floor. So design lateral force, already we have seen that either we can write it down QIK or FIK is equals to AK phi IK, participation factor of this particular node K, right? And your WI. So here QI1 will contain Q11 and Q12. Already we have solved for this example. If you have seen here, design lateral forces for different stories, we are already have solved it for different stories using the concept of this model participation factor already on the previous example. So here, what will be the next step? So you just need to use the information like A1 is given 0.34. This is nothing but the spectral acceleration, and your WY is nothing but MI into G. So you just need to fill up all this equation and solve it. So your Q11 comes as minus 1115.1 Newton, and Q12 or Q21 comes as minus 1463.6 Newton. Similarly, for the first mode, if you consider the first mode and I want to calculate the uh, Storey shear for the second mode, what do we need to do? Again, you need to use this equation Qi2. You will find out the corresponding values like phi 21 and phi 22. By this way, we can calculate the Storey shear. Now, once we have, and using the concept of the response spectrum also. Now, once we have the Storey shear, that lateral forces, here we consider the design lateral forces. Now, once we have the design lateral forces, we can calculate the Storey shear also. So, Storey shear is nothing but we just need to add that to like Q11. We have found that what is the value of Q1. It contained the values of Q11 and Q12, and we have also Q. This is Q. Q2 is Q22 and Q12, right? Now, from the previous example, already we have calculated the design lateral forces. That means we have these two values Q1 and Q2. That means Q11 and Q22, we just need to add them. So the Storey shear will be Q11 plus Q22. And again, for the second, it will be Q12 and Q22. Once we have the value of Q1 and Q2, we can easily add them up to get the Storey shear at each floor. So the Storey shear comes as for the first floor, that means V11 comes as minus 2578.7 Newton, and V12 comes as minus 436.8 Newton, right? So by this way we can calculate the Storey shear for that two particular modes. Now once we have the Storey shear, we can easily calculate what will be the design shear using the SRSS rule. So what we need to do, we need to calculate this. We need to just add like the Storey shear for first node using SRSS V11 square plus V12 square. Again, V2 will be V21 square plus V22 square. Now, if you perform the exercise, you will find that V1 comes as 2615.43 Newton, and V2 comes as 1556.91 Newton, right? So by this way, we can calculate the values of the Storey shear at different modes. So that was all for the how we can solve a multi-degree of freedom system. under earthquake excitation. So first, what we need to do, we need to have the information about the mode shape and natural frequency. Then we need to calculate the modal participation factor for each mode. Once we have the modal participation factor, we can easily calculate the modal responses, and then we add the modal responses to get the total response of the particular system. Now the total response, we have seen how we can use the modal combination rules to have this kind of results, where we have seen different kind of combination rule, SRSS, CQC, we complete quadratic thing we have not discussed yet, but we have seen that absolute sum and how can use that concept of absolute sum and SRSS to get the responses, right? Now we can go to the MATLAB and solve the same thing using MATLAB. And one more thing we left with, like model reduction technique. We will also discuss few minutes, spend few minutes with it, and then we will conclude. Okay, so till now, do you have any kind of doubt? Well, so let's first talk about the model reduction techniques, and then we will go to the MATLAB and spend few time there to solve the examples. Okay, so basically, what we have seen for the MDOF system, the equation of motion M, say x or u double dot of t plus k x of t, and if we have the damping model c x dot of t, this is x of t, okay, is equals to some force, or if earthquake force is acting, so we have minus m into xg double dot. Now here, this m, k and c, is all matrices can be n cross and degrees of freedom. That n can be like 3, can be 30, can be 300, right? Now think of this matrix where this element will be more than 30, 40, 60. Then for these systems, it will be hard to solve it. Now what we generally do, we reduce the size of the this system matrices, so that our final that response or the final answer will sort of not deviate much from our actual results. So how we can reduce these matrices without hampering much the final results? So how we can do it? So there are like two methods are there. One we call the static condensation method, one is called the dynamic condensation method. Now in this static and dynamic condensation method, actually what we generally do, say for example, this is the n degree of freedom system and subjected to some ground acceleration xg double dot of t. Now it has a degree of freedom, n degree of freedom, right? So x, if I want to write x, so we'll have x1, x2, x3 dot 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 xn up to xn. So first, for the model reduction, what do? We first categorize this generalized degree of freedom into two categories. One is called xs, the secondary, and xp, the primary generalized coordinate or primary degrees of freedom. Now we can easily express the generalized coordinate like this, xs and xp. Now for the static consideration case, static condensation case, for the static condition, what we can write, k into x is my f, right? Now Here we have segregated or separated this x as xs and xp. That means secondary coordinates and the primary. So simultaneously we need to separate out the k also. So here the k matrix is also separated or broken into secondary and primary components, or secondary or primary elements. So what will be the first element? KSS, KSP, KPS, KPP, KS, KP is. Also we have categorized the forces acting on each degree of freedom. So we have categorized the force, that primary force and secondary force. So for now the secondary force is considered as 0. That means this is 0. So now if we break it into equation, what we will have? We have KSS into XS plus KSP into XP is equals to 0, and for this KPS into XS, KPP into XP is equals to FP. Two sort of equation. Now here, from here, XS, what is the secondary degrees of freedom in terms of primary degrees of freedom? Well, that will be KSS inverse KSP into XP. That means finally we have the transformation xs is equals to t into xp. The relation between secondary and primary coordinates. This is very important, transformation for the model reduction technique. Now, so that T transformation matrix T is nothing but minus KSS inverse KSP into XP, right? So now we can use or express the generalized coordinates like this. X is equals to xs and xp, so that comes as t into I common xp. So finally we can use this expression, x is equals to t bar into xp, which will finally give us the transformation or the relation between the generalized coordinates and the primary coordinates here, which we will look to consider in our model for the model reduction techniques. Now we can use this transformation like x as secondary coordinates is nothing but the transformation matrix or the transformation vector into xp. So it will be matrix, I think. I not I think it's matrix. It will be matrix, must be. So now using this equation, equation number 3, if we put it in equation 2, instead of xs, this part we will have xps t into xp plus kpp into xp is equals to f. That means the primary uh, generalized coordinate xp comes as kps into t plus kpp inverse into fp. So this actually tells us what is the relation or what will be the primary degrees of freedom or primary generalized coordinates when we will consider the static condensation case. Now we have this matrix xp is equals to kpst into kpp inverse into fp. Now also we have this transformation x is equals to t bar into xp. Now we can easily calculate the potential energy V and the kinetic energy T, right? So the potential energy is nothing but x transpose k into x. If you simplify it, it comes as this, and the kinetic energy half into x transpose into m x dot transpose m x dot, like half into x dot square, and here k into x square. So that things get simplified, and also using the concept of the virtual displacement, if we use it, we can use the get the information about the damping also. So finally, what is the reduced K matrix with respect to the primary coordinates? K will be nothing but T transpose K T, or T bar transpose K T bar. The mass or the reduced mass matrix will be T bar transpose M T bar, and your C matrix in primary coordinates will be T transpose or T bar transpose C T bar. Now finally we can write down the equation of motion in the reduce model, or you know, in the primary coordinates. So MP into x MP value, from here we can get the MP value, x double dot of P plus CP x dot of P, that means in the primary coordinates we are writing KP into XP is equals to FP. Now once we have the this equation, and we have the initial condition for the primary degrees of freedom, like what will be the initial velocity and initial displacement, we can easily calculate using this information. X is equals to T bar into XP. We can have the initial condition. Now once we have the initial condition one and the equation of motion is ready, we can solve it, and we can solve for the responses. What will be the XP of T, or the X of T, corresponding to different degrees of freedom. So by this way, using the static condensation, we can uh, we can use the model reduction technique, or we can use the size of the matrices. Still we will have sort of similar kind of results, because here only we are segregated into primary and secondary coordinates, and we set a general relation between primary and secondary coordinates, and then we solve it, right? Like here for this system also we can calculate. So this was the example already we have taken on the previous class, where we have calculated the natural frequencies and the K matrix. So once we have the natural frequency and the K matrix ready, we can calculate the KSS, KSP, all these things. So KSS, this is your KSS, KSP. Now look for the KSP part. So it will be this, these two part. Now KPS will be minus 150 into minus 150 and 0, this part. Now KPP also we can form. So in this matrix we can write it down like K, we need to KSS, KSP, KPS and KPP. So we need to find out this individual matrices, and that comes as the values comes as this. Now once we have all these values, we can find out the T. That means the transformation matrix. What was that value? T is nothing but XS P. That T, if I want to, that either I want need to do the inversion, or we can do the calculation directly. So the T will be KSS inverse into KSP, and if you solve it, KSS already we have the KSS, we have KSP value, we do the inversion, we will get the T. And T bar is nothing but it's a vector which contain the information about T and I. We can solve it. Like if we consider this example, like the mass stiffness matrix of a 2 degree of freedom system is given. The mass matrix is given as 500, 0, 0, 350, and the stiffness matrix K is also given, like 10 to the power 4, 5, minus 2, minus 2, 2. Now, what they ask here? Consider the first degree of freedom using static condensation method. Calculate the reduced stiffness matrix. Reduced stiffness matrix, right? So the reduced stiffness matrix, what we have seen here, the reduced stiffness matrix is this T transpose K. That means T bar transpose K T bar. We need to calculate the T bar transpose first, and we have the K matrix. So if we can find out the T bar, we can easily calculate the value of this reduced stiffness matrix. So how we can do it? Here, so this is the K matrix. So here we just separate out this K matrix as primary and secondary component, say KSS, KSP, KPS, KPP. Already we have. Now T, is nothing but minus KSS inverse KSP. So we can do the inverse thing. So KSS inverse this, that means the quantity is also given 5 we have. That means the value 1 by 5 multiplied by KSP is minus 2. So that comes as 2 by 3. Now what will be the value of T bar matrix? T bar matrix, we know it's T and this is a vector and I, that means 1. So it will be 2 by 5 and 1. Once we have all the value, so reduce stiffness matrix Kp will be equals to T transpose K T bar. Now we have K trans T 2.51, that means 2 by 5 1, K 2 by 5 1. Now K matrix, already we have the value of the K matrix here. Just do the calculation, you will find out the reduced stiffness matrix Kp will be nothing but uh, almost 1 to triple zero. Just make the calculations right. First do the calculations. Okay, check the calculation step by step. I may wrong, but it comes as 12 triple zero. Now similar way we can calculate the reduced mass matrix also. Here what is the formula for reduced mass matrix? Phi t transpose m t bar. Phi t transpose m phi t bar. So our task is to calculate the value of this t bar. Now how we can calculate the t bar? T bar is nothing but xp inverse into x. So here from this equation we easily calculate kps into t plus kpp into t bar inverse, right? So here two information is important, like xs is equals to t into xp and x is equals to nothing but ti into xp. T is nothing but because how we are finding out this equation, because x is nothing but we have separated out xp and xs. So xs and xp, right? So xs comes as t into xp. So finally that x leads to t in I into xp. So once we can calculate that t or t bar, we can easily calculate the reduced stiffness and reduced mass matrices. So the reduced stiffness matrix we can calculate it like this, and the reduced mass matrix, let's see the values. So reduce mass matrix, already we have calculated the reduced stiffness matrix T bar. So we need the value of T bar. First we need to calculate the T. T is nothing but minus KSS inverse into KSP. Already KSS and KSP you have calculated here. All the values we have. Now T bar also we have calculated. Now once we have these two values, the reduced mass matrix MP is nothing but T bar transpose M T bar. So we have all the values. T bar transpose, that means 2 by 5 1. We have the mass matrix 500 0 0 350, and we have 2 by 5 and 1. Now do the operation, you will get the value for 30. Please check the calculations. So from the model reductions you need to understand how we can find out the reduced stiffness. This is your reduced stiffness matrix. This is your reduced mass matrix, and this is your reduced damping matrix. Great. So for that, what do you need to find out? First, you need to find out the value of t, this t. Once you have the value of t, we use the transformation x is nothing but your this t transpose into xp, and that leads to this small equation tni into your xp. Now, once you have all the information, you can easily calculate the reduce stiffness matrix, reduce mass matrix, and reduce damping matrix. Precisely, that things are done here. We just need to do the calculations. Okay. Now, one more thing we have, like we have seen the static condensation technique. We have also the dynamic condensation technique. For the dynamic condensation technique, uh, instead of using, that F is equals to Ks, we use the free vibration equation. Same thing, mx double dot plus kx is equals to 0. Similarly, the k matrix we have separated out into the primary and secondary component, and also for the mass matrix we have separated out like this, right? Now, similar way we can construct the characteristic equation and solve for omega I. Now here the omega I actually gets solved iteratively. First we need to find out that T and T transpose matrix. Once we have that, we need to use that xs is equals to T into xp. What is the relation between the secondary coordinates and the primary coordinates? What is the value of this transformation matrix? Okay. Now once we have calculated this, we need to calculate MP and KP. Once we have calculated MP and KP, formulate the that characteristic equation, solve for omega. First iteration you get first omega, second iteration you will get another omega, and we will do it until we get the convergence. That means until we will get that final value nearly to the final equation. That means in the model reduction technique we have seen that how we can reduce the mass and stiffness matrix as per our order, so that computational effort should not be so heavy, plus we will get the similar kind of responses. So that's all for today. So what we have solved today, just quickly go through it, then we will close it. So first we have seen how we can, solve um, the response of MDF system under earthquake ground excitation. So first we have seen the concept of the participation factor. Then using this participation factor, we calculated the modal responses to physical responses. Then we have seen how to calculate the equivalent static forces and also the base shear and the base moment. So here not base, it will be the Storey shear and Storey moments at each story. Then we have seen how to use the responses. Like here we have solved this problem and seen that for the two modes we have two modal responses. So how to combine these modal responses to get the final response. So we have seen two or three different methods: absolute sum, square root of sum of square, and CQC method. And then we have solved this example using the concept of the response spectrum and the modal combination rule. And we have solved step by step each and everything up to the lateral forces, Storey shear, and moment. And then we have solved few examples which will be required for your assignment purposes. And that's all. So, do you have any kind of question you can ask me, or today I will end this session? MATLAB thing I will show you on the next class. Today we run out of time and my health is also not well. So, next day we will see the MATLAB part. So, do you have any kind of questions you can ask me, or else we can conclude here? Nandulal.
Yes, sir. Okay.
Yeah. So, have you solved the assignments?
And I've gone through one or two questions. Only I have solved so far. I will, with the help of these questions, I will solve, sir.
Yeah, so yeah, after watching this video, you will able to solve the questions, no issue. So we have solved different problems, and we have already solved using that values also. So just cross check them. Okay, your work is to cross check them. The final results are okay or not, and all these things, right?
Okay, sir. Okay, thank you.
Well, so on the 12th, after 12th week, we will plan one session for the you know which kind of question may come uh, in the final examination. So we will discuss. Okay. So April after 11th. So suggest some dates so that you all people can you know join and interact, like whatever your doubts are, you can get cleared at that
It is
moment.
necessary, sir. It is very necessary for the exam, sir.
Yeah, it's necessary because you have seen that assignment question, it's quite tricky, and like similar kind of question will be there, like if you have if there is no like interaction sessions, and if similar kind of problems have not solved, then I think you will face a lot of problem during your assignment solutions also.
Here, one thing I want to know, sir.
Yeah.
In exam, the question will be similar to assignment, or we have to go through some books or notebooks or
No, no,
some
no, 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 no,
particular.
no, no. You don't need to go through any kind of books. The questions will be similar kind of assignments. And also the questions whichever solved during your lectures, that kind of questions may come.
Okay, sir. Okay, thank you for this
Like,
kind information.
yeah. And don't need to search for different kind of questions. Similar kind of questions, maybe data will be changed, maybe little pattern will be changed. Like in a question, the story share, to calculate the story share, they have asked in the assignment. In the final question, they have asked calculate the moment, base moment. Similar kind of questions. Okay, so but you need to understand the problems whatever given to the assignments very carefully. Then only you can solve within that time. Otherwise, it will be very difficult to solve there within that stipulated time without any calculator or MATLAB. So yeah, you need to practice it.
Calculator also will be not allowed.
Yeah,
Computer.
no, no, no. Calculator, on-screen calculator, they will allow, but if you don't practice with the on-screen calculator, they are useless.
Okay, okay, sir. Okay, we'll practice like that, sir.
Yeah, you need to get habituated with the on-screen calculator. Otherwise, on the very first day, you will just get stuck with that calculator, and you will lose your time. So there will be. I will
Set of
discuss.
questions.
I will discuss the pattern of the question. Like there will be 40 to 45 marks that MCQ type of question, then like 20 or 25 marks MSQ type of question, and then this big type of numerical type. I will share all this information, like what will be the pattern of the question, how many questions will be there, and all of these things. No, no worries. But yeah, we need to schedule one day because after 12 I can discuss that, and I also that day should be aligned with my schedule also, because on that April second week, if I am busy, then I cannot conduct that class because my responsibility is after 12th week, right?
Okay, sir. Okay, next class. Okay,
We will,
you.
yeah, we will discuss
Yeah.
some dates. Okay.
Yes, yes. So better to question and answer group no session that will message sir, and accordingly we can plan, sir.
Yeah, accordingly we can plan. Yeah.
But here, what I'm requesting, sir, one set of sample question now, how it will be there. If it is possible, can you provide, sir?
Sample questions, then I need to like make some sample questions out of your assignments and your that course content. I can do that, but yeah, questions I can make it, but the solutions I need to sit for the solutions also. Solutions you need to take care of the solutions. Then only I can make one or two set of questions like similar, which will align to your final exam.
No, no,
Like
sir, here what you will set the question, will solve and put in the group, and you can check and reply whether we have solved properly or not. Okay, in that way
yeah,
it may help. That is my thinking. I may be
yeah. We can also do that also. Yeah. So okay, then once I have the time, then I will start preparing some sort of questions. Okay, no issue.
here throughout the course, whatever you have solved the questions, there will be the that question together in one file will be there in your.
Yeah, in that drive, not in together. You need to look for different weeks notes. Then only.
That is there, sir. Actually, if all the question will be in single file, na, it will be easy to in
Just
word format na, or
just
text
sit,
format.
spend half an hour, copy and paste all the questions,
Yeah,
and
yeah, that I am doing, sir. But what I felt, then that is I requesting from you, sir.
no, yeah, what I can do, uh, that question should be there, but I can make some additional questions, similar kind of questions, new type of similar kind of questions, and already the questions are there. There are no point of copying and pasting there to make a separate file. But I will make some sample question paper for like 100 marks or the full marks question paper, and then we will discuss and we will try to predict from where the maximum questions may come or which kind of questions may come. We will do that SWOT analysis or the statistical analysis on that class. Okay.
Okay, sir. Okay. Thank you, sir.
Okay
Thank
then.
you.
Okay then.
Okay. Okay. Bye, sir.
Thank you. So we will meet on next interaction session on. Okay. Thank you.